All right, hi there. This is Jacob Nash. We are coming back now, looking at finding volumes with the shell method. In the last video, we looked at finding volumes using the disk and washer method. So, what's the difference? Well, if you remember, what did we do in the last video? We made cuts through the little shape we're trying to find the volume of, and we made them perpendicular to the axis. Remember, I said that. Perpendicular to the axis that we're spinning around. This time, instead, we'll make a parallel. It makes sense. If you're doing it perpendicular, just imagine like a straight line, like hold out your hand in front of you straight up, and then kind of go like in a circle. You know that that would make a 2D shape, right? That's going to make a washer or a disk, depending on if there's a gap in the shape of your function. But if you instead go parallel to the thing that you're spinning around, you're creating a 3D shape. And when you rotate around something completely, that creates a circle. And since the thing that we're doing has height, it makes a cylinder. So, and it's cylindrical shell method, really. Um, well, if that didn't make sense to me just describing it, you'll see how it looks. So usually you can do either method, disk washer or cylindrical shells, but one is easier to do. And that's a matter of if you have to split up the integral, because both of these, when you're trying to find, um, when you're setting up the integral, you usually have to do the top function minus the bottom function. And that can if that changes, then you have to separate the integral into parts. So that's what this is. That's what I'm saying. It's just a matter of which one's easier to tell you which one to use. Usually you can do both, but one would be harder. Like I said, we're going to be parallel to the axis or line we're rotating around. Now, don't worry about all this crap right here. In case I didn't mention it before, these are my old notes that I have in the videos, and I'm doing them like this to try to save time so I'm not drawing everything because that makes the videos way longer. Um, Unfortunately, I can't even really do that now, anyways. Might have said because my iPad's messed up, but here is our formula of how to set up the integral. So this is what you should really look at here. So 2 pi, we just take that out, okay? Um, this is really based off of our surface area function, and if we're taking the integral of it, it makes it volume. Um, but we're taking that 2 pi out because it's constant, so it's really our radius function times the height function. You might, in case you forgot it in the last video, why is it Rx? What does that mean? And what does Hx mean? Well, that's because our height and radius are not the same. Like, remember, we're making an infinite number of cuts. That's what this thing is saying. If you make an infinite number of cuts in this interval and you make them parallel around this axis, what is the volume you'll get? That's what this thing means. So that's why it's R of X and not just R. If it was just R, that means it's only at one place. R of X to say, hey, this is a complete function, that we're thinking of. And I'll tell you how to find R of X and H of X. It's not really too bad. So let's keep going. Okay, here's our question. Find the volume bounded by this function here, around the line x equals 6. Now, it doesn't tell us that we're supposed to use cylindrical shells, but we are because that's what I'm teaching you. But like I said, you could do the disk and washer method on this, but we're just going to do the cylindrical shells in this case because it's easier, and that's what I'm teaching you in the video. So, yeah. The first step is to find h of x. That's saying what is our height function? Always what it's going to be is the top function minus the bottom function. It's that simple. Uh, there you go. That's the higher one. The blue one is always higher minus the red one. It's always lower. Bingo, right? And let me explain why, because sometimes it's not enough to just know that it's that simple. How come that this is what it is? Well, this is the value we're trying to find. That's what h of x is, the height in between them. And by the way, notice how it is parallel to what we're spinning around. And I'll talk about later in this video how you know to be in terms of x or y, because we could have h of y or r of y, but it's h of x because if you're spinning around something vertical, it's always going to be with x's in the equation. But we'll get to that, so don't worry about that yet. So we're trying to find this yellow. How would you find that? Well, this whole thing is going to be what? This function, right? Because that it's what is the function saying? Y equals that. It's saying the Y value is that. That's why this value is that function because it's a function because it changes throughout this region, 1 to 5, right? It changes. So that's why it's a function, not just a value. So we're saying that's that function. And then from here to here is just a red function. So in between you do big minus little. That's why we do that. But if you don't care about what I just said, if you're like, I don't get that, that does just remember top minus bottom function. Top function minus bottom function. It's that simple. And if you notice that it changes, that's where you have to separate the integral, and it might mean this can wash the method's easier. But not in this case. Now, how do you find radius? Uh, the radius function is if you're rotating around an axis, it's just going to be x or y. Like I said, I'll get to that in a second. But since we have this 6, we're rotating around 6, that's it's not going to just be x. It's going to be 6 minus x. Now, you might be thinking, well, wouldn't it be 6 plus x? That's easy to think since this is in the positive direction. But no, because once again, isn't this whole value 6? Isn't this whole value x? Wherever we are, it's always going to be the x value. So 6 minus x is 6 minus x is this region here because we do the full thing minus the little thing to get us the in-between thing, because this is what we really want to know. So once again, if you don't understand that, if that doesn't make sense to you, just remember it's always going to be a number. Well, I wouldn't, it's not going to always be a number minus x, depending on where it is. But in this case, you would have to know that's what it is because, uh, that's really the only way you can think of it. This full thing is 6. This small thing here is x. So the in-between part is 6 minus x. This is why it's really good to sketch. So if you sketch it, it's easier. Now we just plug those two freaking things into here. Our bounds are 1 and 5. Now, how did I get that? The only way to know was to set these equal to each other. That's how we find our bounds. So I should have said, technically, there's three things to find. There's this, and then your bounds. Um, so I set these equations equal to each other. The easiest thing to do is to get rid of that square root, so I square both sides. So I have 4 times x minus 1 squared. Uh, Put that on the other side, and then this is a little crazy, but you can actually do this. You can factor out an x minus 1, and then you end up getting 1 and 5 as the places where they intersect. And remember, that's the point, because we want the places where it stops and ends, where this like leaf-shaped thing stops and ends. And so we have 1 and 5. And then we multiply the Rx and the Hx. And I'm not going to show you how to anti-derive or do the antiderivative because hopefully you know, but in this case you would actually have to use U substitution. So there you go. You kind of have to remember things from the past videos, but that's how you set up the integral, which is really the only purpose of this video. So now we're going to look at an example where you can do how I'm showing you that you can do either way, but it's harder to do one way than the other. Um, Now, actually, before that, I'm going to say this. So, how do you know if it's going to be, in terms of x or in terms of y? Meaning, sometimes you have, remember how you can have r of x or r of y. How do you know which one it's going to be. Well, let's start with the discs and washers in the last video. If we're going around the x-axis or around anything that's horizontal, solve for y. So solve for y is going to mean it's in terms of x. So I know that's just very annoying, but you kind of have to just get used to that. That's what it means. So if we're solving for y, it's in terms of x because all the terms have x in them. So it's going to be y equals something. But if you have to go around the y-axis or around something that is vertical, a vertical line, then it's going to have to be in terms of y or you solve for x. So you're gonna have to change your equation to like x equals square root of y or something like that. And then cylindrical shells, it's reverse. If I'm going around the x-axis or something that's horizontal, I will solve for x. And if you're going around the y or something that's vertical, just like in this example, it's vertical, it's you solve for y and you don't always have to because it's in terms of y already. I mean, it's in terms of x, it's solved for y already. So if this kind of confuses you, I would just really write this down. If it's in terms of y, you solve for x. If it's in terms of x, you solve for y. I know it's annoying, like to remember, like that seems like very like if you're not used to that terminology, you might think that sounds like backwards or something. But like if you just remember these things, you don't have to really know that in terms of. But in terms of what that means is what the things are after the something equals. So y equals x squared, for example. That's in terms of x and it's solved for y. If it's solved for x, it's in terms of y. So it's it's backwards for discs and washers, but it's the same for cylindrical shells. Typically, you would want to solve for y because you don't have to do anything. It's usually already solved for y. You know it's solved for y if it says y equals. You know it's solved for x if it says x equals. I'll put it that way. Um, I don't understand why they have to have so many different ways to say the same thing, but that's all it is. So we're gonna, go back to this now. And I hate that all these examples are all in terms of x because I wish there was one in terms of y because that definitely can happen. But let's look at this example. So we're trying to find the volume of this region and we're going around the x-axis. Okay, well let's see. We're gonna do shell or sorry, washer on this one. Okay, discs and washers, we're going around the x-axis. We solve for y. It's already solved for y. See? Y equals y equals. So we don't have to do anything. And basically we learned in the other video how we would do that. It's big radius minus small. Here's the big radius, top function minus bottom function. Squared, though, it's always squared for discs and washers. And that's better because if we here, what would we have to do if we were doing shell method? Well, for shells, if we're going around the x-axis, we have to solve for x. So we'd have to change these equations and solve them for x. It's really the only reason why that would be. Oh, also the top curve changes because if you're doing cuts that are like this, um, the one that's further out changes as you go. And you would see that if you're doing that, but you can visually see that it's possible to do the washer method. So that's why I would do it. Now, if we had a part B that says around the y-axis, um, what would that mean in this case? So this time we'd want to do the shell method because it's reversed. If we're around the y-axis for discs and washers, we have to solve for x. That's kind of annoying to do, right? So we don't want to do that, so let's do cylindrical shells. So I don't really care. I mean, top curve changes, that doesn't really matter as much. It is more work to separate the integral. But for me, I kind of think of it as, dang, do I really want to have to change it up and solve for x? So if I'm going around the y-axis, I probably do want to do shells, but not always. But in this case, yes. So same thing as before. What's our height? Top function minus bottom function. So top function minus the bottom function. The radius is just this, and it just is x this time. The radius is always going to be the middle. It's going to start at the thing that you're rotating around, and it's going to go to the first line that you hit. So this is the radius, r, and it's just x. There's no reason to transform it, or like you see how we had it six here, and we had to do 6 minus x. Don't have to do that this time because it's just the y-axis. So we multiply those things for that. Now it's saying what would you do if you were going around the y equals or the x equals 5? Once again, since this is a vertical line, vertical lines solve for y. It already is solved for y. I don't have to do anything. And then y equals 8, that's a horizontal line. Horizontal lines solve for y for discs and washers, so we use discs and washers. So that's basically the end of this video. I apologize. I tried to be as clear as I could for this. This is probably one of the more maybe confusing things that we have to talk about. But I would just really write down this thing right here. And hopefully you realize that it's really not a hard process. But this whole thing on this slide is just about how you can know which one to do. Like which one might you do. And like I said, it's just a matter of which one's easier. If you do the wrong one, there's no wrong way, but it will just you'll figure out that it's really hard to figure out what R of X is or H of X or something. That's how you'll know that it's not the best choice. But to recap, kind of for both of these methods, remember for shells method, for both of them, if to find where it starts and ends, you set the equations equal to each other. Um, And then for shell, or sorry, for discs and washers, um, you you have to find you do the big radius minus the small radius, both squared, and you have pi on the outside, only pi. You have 2 pi for this, only pi, because the equation we're based off of for this is area, 2D. This is based off the surface area because once again, we're creating a 3D shape here, 2D shape here. But you have to find, you basically do big radius minus small radius, squared both, and you have that pi out there. For this one, you have to find what the radius function is and the height function. The radius is just, you'll always just see what it is. You might have to add, you might have to do something like that, 6 minus x if it's not the axis. For the height, it's easier. You just do top function minus bottom function. Multiply those together, you have that 2 pi out there. No need to square this time. And there you go. So that's it. Like you just those are the steps you do. You just have to find those things and there you go. Go from there.